Hi ladies and gentlemen, we're going to take a look at two other canonical partial differential equations today. We've been studying the heat equation. Today's topic of conversation are the Laplace equation and the wave equation. So these three equations together form the most basic examples for parabolic, elliptic, and hyperbolic PDEs. Starting with Laplace's equation, there was an introductory video here that talked a little bit about what Laplace's equation is. I'm just going to read through. I'm actually going to read my notes. Laplace's equation on a rectangular region has four boundary conditions, so it is a two-dimensional equation. There is no time dependence, so it's only a spatial equation. And in general, it's a function, the temperature function is a function of x and y. So we don't have any initial conditions, we only have the boundary conditions. And the equation tells us that we have zero net flux of temperature through the region that we're considering. And so there's no temperature source or sink that's internal to our rectangular region. And all of the temperatures inside of the rectangular region are determined by the boundary. So this is a steady state condition that is in place because of the boundary conditions. Looking at the PDE here, what it really comes down to is this is the steady state 2D heat equation. So you recall the heat equation in general for 1D is something that looks like this. And this is where u is a function of x and t. And so we've been looking at this problem for quite some time. It's not a big stretch to think instead of looking at one-dimensional heat flow along a rod, for example, we could consider two-dimensional heat flow through a plate. So we could have temperature that is moving around in a two-dimensional plate. And what that means is the temperature function would look like this. And the extension of the heat equation is quite simply ut equals k times, and now I have two partial derivatives with respect to the spatial directions. I have a uxx and a uyy. And in the situation that we have with Laplace's equation, it's just steady state. So this part here is zero. We have no evolution of the temperature with respect to time. And then of course what that leaves us, we could divide the k over, and that leaves us with Laplace's equation, which is nothing more than uxx plus uyy is equal to 0. So this is really the most basic elliptic partial differential equation, and it has a lot of application, as well as its extension, which is the Poisson equation, where we have some kind of forcing here. So we have an equation that is not homogeneous, and that's called Poisson's equation. So in general, the information that we received from the video, he talked a little bit about this, and also the whole idea that we know the Laplacian is the divergence of the gradient. And because the divergence of the gradient field is 0, there's no net flux across the boundaries, so into or out of the situation. So we could have, and there are some simple examples, right? We could have something in here that's generating heat. That's a very common problem. That's the Poisson equation, where we have in here some function, and it wouldn't be u, but it would be some forcing function, and it could be a function of u, it could be a function of position, it could be a function of time, it could be a function of anything that is an internal heat generating type of an item, and that would replace the 0 over here. And that would give us Poisson's equation. But we're not going to study that. I'm just letting you know where that relates to what we're doing. So that's really just the introduction of Laplace's equation. Now we talk about the wave equation. And again, a nice video kind of giving you the introduction to the wave equation. We talked about this a little bit previously, and let me just reiterate what it was that we discussed, I think maybe last time. From a conceptual standpoint and understanding, let me switch over here. remember again the heat equation, UT equals KUXX, and I asked you several questions last time about what do you think it would mean if we had a acceleration instead of a velocity that was proportional to the curvature of whatever it is we're talking about. And as we discussed last time, this is the wave equation, and you saw that in your solution here. So with respect to the physical understanding piece, it's exactly what we discussed last time. There's no exponential decay term, which comes from this first partial with respect to t, but rather acceleration terms, which give us sines and cosines. That's the second partial with respect to t. Looking then at the solution techniques, what I've done here is followed the kernel's flow for the 7 steps that she has, and it's the exact same flow that we did for the heat equation. This is generally why we study the wave equation right after the heat equation, is because the analytic solution methodology is exactly the same. So we're going to figure out how we're going to approach the problem. We're going to assume a product solution and then modify the problem given our assumption of product solution. We're going to separate the variables, and we're going to build 2 independent ODEs, one spatial ODE and one temporal ODE. And then in step 5, we're going to solve those 2 ODEs, starting of course with the spatial ODE. That's what's going to give us our eigenvalues and eigenfunctions. And then in step 6, we're going to build the product solutions, and then we're going to take those product solutions under the principle of superposition and create a general solution. And then finally, we'll apply the initial conditions in order to find the constants. Question here about what do the terms in the equation mean? And again, I'm just going to read this to you. The function u, a lot of textbooks will use y because it's literally vertical displacement that we're talking about. The function u represents the vertical displacement of a homogeneous massless string, so there are a bunch of assumptions about the type of string that we're using. The local acceleration of each segment of string, which is the second partial of u with respect to t, is proportional to the string's curvature. Let me put the appropriate mark in there. The string's curvature at the same segment. So the greater the curvature, the faster the acceleration. And the proportionality constant that it relates these 2 items of acceleration and curvature is the wave speed, which means the acceleration is greater for the same curvature when the wave speed is higher. This kind of meets with what we would have for a basic intuition. And typically for the boundary conditions, unlike the heat equation, we generally have Dirichlet conditions here, which are homogeneous, so they're both equal to 0. That's not always the case, but when we have problems like the hanging chain problem, which is a different differential equation actually, but when we have a problem where we have something like this, where the chain is hanging down, and then we have a free boundary down here. So our boundary conditions were generally fixed up here, but we have a free condition down here, and we can model the behavior of a chain that's linked together. That's an interesting, it's an interesting result when you go through it for the first time. So the closed form solution, this is exercise number 3, and of course the kernel goes through the same steps. I've written my steps to match with hers, just a little bit more emphasis on the fact that steps 3 and 4 to me are really kind of done all simultaneously, and then steps 5 and 6 are much more significant and have to be done kind of in multiple steps and in the right order. So this is the complete flow for the problem, the worked example in 13.4. And I'm not going to go through all of this. I will go through this slowly so that if you want to look at it, you can at a later time. But because the homework problem is nearly identical, I'm going to wait to explain what all these steps are and how they are the same or different from the heat equation once we get there. So again, this is the worked example that's in the textbook. And there's a little bit of a nuance when we get to step 6a, which again, it's not in this portion, but I'll talk about it when we look at the homework problem. And of course, at the end of the day, we solve for the constants after we've applied the initial conditions and end up with things that look like Fourier series. So there are some solutions here from the kernel, and now it's time to take a look at the homework problems. So for the first homework problem, compare and contrast the heat equation and Laplace's equation. This is really what I was trying to address at the very beginning. The heat equation and Laplace's equation are basically the same thing. The difference is that the Laplace's equation is the 2D heat equation held at steady state. So there's no evolution with respect to time. And if you think about what that means to the 1D heat equation, so I've said here, consider the steady state 1D heat equation. U would just be a function of x, right? It would no longer be a function of t because t is not an independent variable. Nothing's changing with respect to time. So we would just end up with the boundary value problem that we were looking at in section 3.9. And that's really the backstory of the steady state 1D heat equation, is simply looking at an ODE where we're considering boundary conditions. And there's really nothing revolutionary in that concept other than to say that we are again considering something like this, and Sanderson talks about this in his video, how there's really no reason we couldn't extend the Laplacian so that we end up with ut is equal to k, and we have the Laplacian applied to u, right? So this is the multi-dimensional heat equation, and in this case it would be the three-dimensional heat equation. So I'd have a volume where the temperature inside the volume is changing. And Laplace's equation for 3 dimensions would simply be making this 0, which means I could divide out by the k. I could divide the k out and I would end up with something that looks like this. So that's my Laplace's equation, and I can have as many spatial dimensions as I want, 1, 2, or 3. It's all Laplace's equation. So some engineering examples. I think engineering examples of the 1D heat equation are a little bit more difficult to come by, just because we don't really study the flow through long, thin rods very much. But anytime we have one-dimensional heat flow, we can look at it from this perspective. So even something, for example, where we have a couple of plates that are close together and they're at different temperatures, and we have heat that's flowing from one plate to another. That would be occurring in one dimension, and we could use the one-dimensional heat equation in order to study that. So that's fairly straightforward. And then the Laplace's equation would be any flat surface, right? So we could look at a steady state. Now, granted, this is a little bit different situation, but the steady state, for example, within any integrated circuit. But the reality is integrated circuits are like Poisson's equation, where there's heat generated internally, and so we would have to study Laplace's equation with that forcing included, which then makes it a non-homogeneous equation. So we're going to take a look at this schematic that the kernel's thrown up here, and I want to point out an error that was in the problem. Maybe you caught it, maybe you didn't. Let me paste in here, and I'm going to resize this image. To give me just a minute. I have to make this a little bit larger for us so that we can poke around with it a little bit and put this into place. So what we have in this situation is a standard rectangular Laplace's equation. Now, we don't study this in this course, and we do in 469, where we look at Laplace's equation in circular domains instead of rectangular domains. So of course there are a lot of applications you can imagine where the actual domain of interest is circular and not rectangular. We also look at the 2D wave equation, right? There's nothing prohibiting us from saying, wait a minute, we have a heat or a wave equation that looks like this, but why not again include the Laplacian and have a two-dimensional heat equation. So we look at things like vibrations on drum heads and things like that, because that's a two-dimensional wave equation. So back to this part C here, we have the conditions that are given to us, and you just need to be comfortable in making these adjustments for the conditions. And I'm going to try the green pen. Hopefully that one will show up pretty well on this light background. And so it tells us that when y is equal to 0 and y is equal to b, things are insulated. So y is equal to 0 is the x-axis. So down here, this surface is insulated, which if you see it in a diagram is generally drawn like this. And the top is also insulated. And what that means, of course, is there's no heat transfer through those boundaries. And that heat transfer would be in the y direction. So what we're really saying is that u partial with respect to y, where for all the x values, but for y equal b, is equal to 0. So reminiscent of our insulated ends on the 1D heat equation, that's exactly what this is saying. Similarly then, I would have u partial with respect to y, x, all x values, y is equal to 0 is equal to 0. Now I have the conditions where x is equal to 0 and x is equal to a, and it tells me along the edges where x is 0 and x is a, the temperatures are maintained at 0 and some function of x respectively. So this side is held at 0 degrees. This, however, cannot be a function of x, right? X is equal to a along this entire boundary. So that was really a typo. This is some function of y, where I would have a temperature profile along this edge that changes as y changes. That's what makes sense for this problem. And so I've written out the correct solutions here. And look, if you didn't recognize that variation, that it's no problem. Just understand that it only really makes sense for us to discuss a variation in y when x is fixed. So along that line, I have some problems for you to consider, some different boundary conditions. So at this point, we'll pause the video and you can take a look at these three conditions. I recommend drawing the picture similar to what the kernel has here and just putting into place what these different boundary conditions are. And we'll be back in just a minute. All right, let's take a look at the first one. I chose this first one because this is one that actually has a variation in the x direction. So the first condition says that the temperature when x is 0 for all values of y is 0. So the position where x is 0 for all values of y is the left edge here. So the left edge is set at 0. The second condition says when x is a for all values of y, that's the right edge over here, that again, the temperature is 0. Forget the little Q here. Q is my pause button, so every time I hit the pause button, it throws a capricious Q out there. Then the next one says that the temperature for all values of x when y is 0, that's the bottom, is some temperature of profile g of x. And now we can clearly see that this would make sense to vary as x varies. And then for all values of x when y is b, the temperature is 10. This is a typical Laplace's equation type of situation. We have something that looks like this. I'm going to do the second one and then I'm just going to leave it there. So the second one, I'm going to switch over to my green pen. For the second one, again, x is 0 for all values of y is insulated. X is 0 for all values of y is insulated. This side is insulated. And then over here, when x is a for all values of y, again we have 0 degrees. So that stays the same. Then when for all values of x when y is 0 we're insulated. So that would be down here. This edge would be insulated. And then the last one is for all values of x when y is b, we have g of x. So instead of this, we have now g of x across the top. So that's the idea of how to interpret the problem and its associated boundary conditions when we're talking Laplace's equation. Let's move on to the next problem, 35.2. So this one was taking a look at the initial condition, and I used MATLAB to draw the picture here. So I'll execute the code and the picture will pop back up for us. A couple of things to note, and I apologize, I know my head's in the way of the part of the picture there. We'll talk about that in just a second. But so the boundary conditions, because the question asks about the boundary conditions are Dirichlet conditions. Okay, they are homogeneous conditions. And so I signified that here by in the graphic. Oh, sorry about that. I wasn't able to get the graphic to work out the way I wanted to. So in the graphic, what I've indicated is the fact that the boundary conditions are satisfied. So the red circles show that at the boundaries of x, when x is 0 and x is 1, the initial or the boundary conditions are equal to 0. So the initial condition actually satisfies the boundary conditions. And this is certainly what we desire, because otherwise we have a problem that is inconsistent, although those inconsistencies are generally taken care of when we solve the problem. So in this case, we have the Dirichlet boundary conditions that are set equal to 0, which is typical for the wave equation. And then we have an initial displacement, which is given by this graphic here, the parabolic displacement. And in this case, I just picked an L value of 1. And so we would have, right, in general, the amplitude here would be at L over 2. So we have to put an L over 2 in here. So I'd have an L squared over 4, 1/4. That would give me an L squared over 16 in general. That would be the amplitude that I have up here. And we see here it's 1/16. Also, there's no initial velocity. So the g of x function, as the book references it, would be 0. So now we want to solve this, and I want to walk through all the detail associated with solving this problem. So let's take a look. First things first, of course, we want to write down what our problem is. I've made a change from a squared to w squared as it relates to wave speed, because I'm using a for my alpha, so I don't have to type a bunch of alphas. Obviously, it doesn't make any difference. There's this kind of ridiculous desire by everyone to use the first letters of the alphabet and the last letters of the alphabet, so I'm going with W, which has nothing to do with any of the problems we've been talking about so far, so hopefully it's unique enough that we won't get confused. Boundary conditions are Dirichlet conditions. That's not at all surprising. And then we have an initial distribution, which is the picture on the right, along with 0 initial velocity. And our approach methodology is going to be very much in line with what we did for the heat equation. So the first thing is we're going to write down the problem and figure out how we're going to approach it. Secondly, we're going to assume the product solution. This is the part that we have control over, and we are deciding that we think the solution will be a product of some function of x and some function of t. And then an equally important piece of this is once we make that approximation, we need to go back to the boundary value problem, the PDE, and we need to convert that over. And so in doing so, we end up with all of the information here below 2b to include transformation of the boundary conditions. And we notice, as we discussed last time, that when we're in the situation where we have x of 0 times t of t equals 0, that this situation implies to us, that's not a q, it's a 0. This implies, of course, that we have to have x at 0 equals 0. Otherwise, we end up with the trivial solution, which is not a problem, it's just not interesting to us. And then there's no need to convert the initial conditions. The initial conditions are, just as they were with ODE, something that we apply once we have the general solution. So steps 3 and 4, I combine those together. We're going to separate. We're going to recognize the fact that here we have a function of t, and that's equal to some function of x for all values of x and t, and the only way that's possible is if they're equal to a constant, and again we pick negative lambda as our separation constant. That gives us two ODEs. So the first ODE is the spatial ODE, and that is a second order ODE, and the boundary conditions apply. And this is the value of transforming the problem itself with our product solution assumption, is we see clearly that the boundary conditions apply. And then we also have a second order ODE for the time function, and there are no conditions for that. We're just going to find those and then go back to the product solution. So in part 5a here, we're going to solve for the spatial values, which are really, we're solving for the eigenvalues and eigenfunctions. That's what this comes down to. So we consider our three cases. As we've looked at repeatedly, 0 is not an eigenvalue in this situation. There are no negative eigenvalues in this situation. We have only positive eigenvalues. So as we go through and apply the boundary conditions, we end up with this expression for alpha here. And this is a big conceptual piece as we move forward, is the fact that we were looking for A's, but we found A sub n's. And what I mean by that is we were looking for one eigenvalue, but the reality is we found an infinite number of eigenvalues. And so those eigenvalues, which I'm writing out here, are integral to the solution, and we see that when we get to solving the temporal ODE. So to finish up here, I want to write down what my eigenfunctions are. I don't need the constants because any constant multiple of an eigenfunction is an eigenfunction, and I want to make sure that I understand that there's an infinite number of them and clearly mark in all of these conversations n is a natural number. Now, you notice that we start with n as an integer, but as we discussed previously, if I have sine or cosine functions as my eigenfunctions, those are even and odd, and there's nothing unique in the differences between the even and odd portions. They're all the same eigenfunctions. Let's see, so the second part of step 5 then is to solve the temporal ODE now that we have the eigenvalues. So in this situation, we're now solving a second order ODE. This is where we diverge from what we were doing with the heat equation. The result are two separate solutions. So you've not seen it written this way. But if I've solved the problem t double prime is equal to negative, let me drop the n for a second, just a squared w squared t. If I solved this and I asked you what the solutions were, you would tell me that there was one solution, t1, function of t, which is the cosine of awt, and that there's a second solution, t2, which is equal to the sine of awt. And then, if I asked you for the general solution, you would take the linear combination of these two solutions to build the general solution. In the situation that we have where we have an infinite number of A values, because we have an infinite number of eigenvalues, then what we really have is we have two separate solutions for each n value. And you could label them however you want. I've just chosen to put it in a subscript with a comma. You could label them in any way. But the point is, these are really separate solutions. And nobody tracks them this way, right? The standard way of doing this is to actually build a kind of general solution that's for each t sub n before we proceed. That's not necessary. In fact, I don't even necessarily think that that's a good idea, but this is what everybody does, and so this is what I've done as well, right? Is to build, well, how do I build the general solution? I have some constant times the cosine of a n wt, and then I have some other constant times the sine of a n wt. So for a specific n value, I've built a general solution for the temporal differential equation, but the reality is each of these constants is different for each n value. So for each eigenvalue, I have a different set of constants that's giving me this kind of middle of the ground general solution. So that I wouldn't do it this way, but I'm just repeating what you will see basically in every textbook that you ever read on this subject. And what that means then is, so we're done. We've found the eigenfunctions, x. We've found the associated t solutions for each eigenvalue. And now we're going to build the product solutions. So using the standard format, we end up with product solutions that look like this one here, where we just have to be honest with ourselves. These d's, these constants, not only are they different for each n value, however, they're different from one another because of this kind of midterm general solution thing we tried to build in t. And then finally, the second part of step 6 is using the linear homogeneous nature of the partial differential equation in order to build the general solution. And that means every one of these solutions here, every one of these solutions gets multiplied by a constant and then summed together. That's how we build the general solution. So that's what's happening here. And we combine the Cn, the constant from building the general solution, with each of these d's to come up with, of course, different constants a sub n and b sub n in all of these situations. So let me just show you what I would argue is actually going on here if we were to do this in the manner that we are accustomed to thinking about things. And that's just this little highlighted piece right here. So a really more accurate way of thinking about this would be to do the following. I have my eigenfunctions, and then I have two solutions to my t ODE. I have my 1's and my 2's. And now I think about building the product solutions, and when I do, I have product solutions of the sine of n pi over Lx along with the cosine of n pi w over Lt, and I also have solutions that are sine n pi over Lx along with sine of n pi w over Lt. And these are all solutions, right? This individual thing solves the differential equation and it solves the boundary conditions. Same with all of these. And so now what I do is actually apply the general solution and take the linear combination of all of these things. And if I were to do that, and there are many ways that I could write it, I wrote it in this form here, but I multiply every one of these solutions by a constant and sum them all together. And then of course we're going to end up in the same place. We have to end up in the same place. It's just that it kind of shows, I think, in a little more open manner what's actually going on, instead of that interim step where we build the pseudo general solution for the ordinary differential equation. So look, I'm not recommending you do it this way. I just want to make sure that you understand what's actually going on when we solve these problems. So finally then, step 7, we have the general solution. We're now going to apply the initial conditions. So the initial displacement, we have that function. We set that equal when t is equal to 0. So coming back to the general solution, when t is 0, the cosine becomes 1, the sine becomes 0, and I'm just left with the a sub n's. And then to solve for the initial velocity, I have to take the derivative of this equation. The cosine is going to become sine, and I'm going to evaluate it at 0, so that term is going to go away. The derivative of sine is cosine, and the chain rule is going to pop an n pi w over L out front. And then the cosine evaluated at 0 will be 1, so I end up with this kind of an equation down here. Then what we do is recognize that these look like Fourier series. And what we want to do is use the sine n pi over Lx as an orthogonal basis. In order to do that, we have to dictate. So we get to assume a product solution, and we get to dictate what the inner product is going to be. And we pick an inner product that makes these eigenfunctions orthogonal. And once we do that, then we really do have Fourier series. and we can apply the same techniques that we applied previously in order to find the constants. So I think personally that this is worth a little bit of review here, just to make sure we're clear on exactly what it is that we're doing. So let me just dig into this a little bit more. We have x over 4, and then I have an L minus x, and that's equal to this sum, n equals 1 to infinity, a sub n sine n pi over L x. And what I'm doing is really reviewing for the GR. So remember what we're going to do in order to isolate the a sub n so we can calculate the value for a sub n. We're going to take this and we're going to multiply both sides by sine of m pi over Lx. So we're going to do that on both sides of the equation. Sine m pi over Lx. I apologize, that's a little bit tight. Then what we're going to do is we're going to apply our inner product from negative L to L dx. And the same thing here. I'm going to integrate both sides, negative L to L dx. Now we didn't discuss the subtleties here, but it turns out that I can swap the order of summation and integration. I can push the integral inside even though I have an infinite sum. The reason that that's true vastly exceeds this class. It's a real analysis argument on uniform convergence of this series. But the result is we have minus of our sine, and we have an m pi over Lx times x over 4 times L minus x dx. And because of the orthogonality of the sine functions, the only term that's left over here is the am integral minus L to L. So as I sifted through all these n values, the only one that's non-zero is when I have m equal to n. So we have this situation here, Lx dx. Sorry about that. With our dx. And so this then is how we end up with so we can change m to n, right? That doesn't make any difference. That subtlety is generally lost in this conversation. But the point is, it doesn't matter what the index is. For each value, for each one of these basis functions, we can find the constant as this integral from minus L to L sine of m pi over Lx, sorry, in this case now it's back to being an n, times our f of x, x over 4 L minus x dx. And then we're going to divide by this thing here, and you remember this item here is just equal to the L. So this thing simplifies to be just L, so we have a 1 over L. And then the reason we end up with a 2 over L, 0 to L, is because this is necessarily something that is odd. We've made it that way because we chose the inner product to go from minus L to L, and we multiplied by some sine function. So it's called a half-range expansion, where we've taken this function, which initially is only defined from 0 to L, and we have forced it into an odd extension between negative L and 0. So if you don't understand those subtleties, that's okay. I don't think that subtlety is necessarily part of what we're after here. We didn't spend a lot of time on half-range expansions. But by virtue of the fact that I have chosen this, I am forcing what this function is going to look like between negative L and 0. And so this is where the term comes from. So this is just a little review of how we work Fourier series to come up with our expressions. And that's the solution. And of course I want to give you an example. I picked an L value of 1. I picked a W of 2 for the wave speed. Given that, I come up with this a sub n, which doesn't look anything like the one that I have written down. However, it's mathematically equivalent, of course. And the three-dimensional picture for the wave equation looks like this one here, where it's difficult to see because there's not a lot of displacement. Let me execute the animation here. This might make it a little better. Okay, that's the initial condition. And then once that releases, we have oscillations that look like this one here. So this is what the wave equation gives us. Given some initial conditions, we end up with an oscillating string. And again, that one's not great to see. It's much easier to see if we remove the division by 4. If we just make this division by 1, then the amplitude is going to be significantly higher, and we can get a little bit more detail, and we can see here that the amplitude is larger. So when we look at the animation, it's going to look a little bit better. If I can get out of the way of it, which I can't. And what you notice is it's interesting, the parabolic part here, it's not just a straight up and down like a sinusoid. There's a little bit of flexure here as the wave goes back and forth. And again, that's because it's parabolic and not a sinusoid for the initial condition. So finally then, the last homework problem is 35.3. In this situation, it's just about you basically coming up with this function here. That's what the kernel was after. So sure, write down what the equation is, write down the right boundary conditions. So the verbiage tells us the string is tied to the x-axis at 0 and L. So that's going to give us the 0 boundary conditions, the Dirichlet conditions. And then the derivative is equal to 0 because it says the string is released from rest. So it starts at rest, so there's no initial velocity. So really the item is converting the picture into this formula. And again, you can pause it and look at it if you want to when we go through the video, but this is what the initial condition is, and all I did was set up something here that throws out a couple of random values for L and H in order to give us a picture. And here's my hat picture, and unfortunately I can't get my head out of the way because I can't scroll this anymore. But this just shows that sure enough, if you give me the right L and H, or any L and H, then the function that I have defined up here will give me the hat function that was provided in the example. So with respect to points distribution, we have what looks like the bulk of material is in the second problem here. So let's go with a 2, 4, 2 for the points. This middle section is really the meat of the situation. You do have to understand Laplace's equation. I'm quite certain that's going to show up on the GR, probably because we haven't solved it. It's going to show up as conceptual questions, which is why I wanted to spend some time doing things like this. And then the heat equation, as you saw, walking through this now, looks very much like, the wave equation looks very much like the heat equation until we get down to solving that ODE for time. And then that's going to drive us to a different looking general solution where instead of having an exponent, an exponential in t, we have sines and cosines in t, which follows with our intuition that the string should be vibrating. All right, thanks very much, and we'll talk here in just a minute.